Alright, in this video we're going to be covering the 4 possible types of titrations with a weak strong titration. So in this case we're working with a strong titrant, that being potassium hydroxide, and a weak sample, that being ethanoic acid. Okay, so we're going to do parts A, B, E, and F, as C and D are pretty repetitive. So let's start with part A. So that's 0 milliliters of titrant, so 0 milliliters of potassium hydroxide, and we want to find the pH of the solution. So we're just going to look at the sample, right? Because that's the only thing that's in the solution, right? So it's just a simple dissociation ice table, right? So our ethanoic acid, that dissociates into a hydronium ion and an ethanoate ion. Initially, we have 0.2 molar, right? So minus X, 0.2 minus X. And for the hydronium, we have 0 initially, and the ethanoate ion, we have 0, plus X, X. It's pretty self-explanatory, right? The Ka of this is 1.8 times 10 to the negative 5. That is clearly a lot greater than 0.2. So that means that this X is pretty much going to be negligible. It's 0.2 minus X is approximately going to equal 0.2. However, this X will still be pretty useful for finding the hydronium concentration, which will give us our pH. If we rearrange the equation, right, X, so let's write this in white, X equals the root of Ka times the ethanoate ion, times the ethanoic acid, and then X equals the root, so Ka being 1.8 times 10 to the negative 5, and our concentration of our ethanoic acid, 0.2, right? We got rid of the X because it's negligible. So if you put that into your calculators, your X ends up being approximately 1.88 times 10 to the negative 3 molar. And remember, your X is also your hydronium, so your hydronium ends up being 1.88 times 10 to the negative 3 molar. And your pH is just the negative log of that, right? So your pH ends up being negative log of 1.88 times 10 to the negative 3. And your pH should be about 2.72. So that is your pH when there is 0 titrant in the solution, and we're just working with the sample. Okay, so this is part B. We're going to be working with 0.05 liters of titrant this time, with our titrant being potassium hydroxide. And I'm just going to tell you right away that this solution is going to be dilute, meaning we can add more potassium hydroxide or titrant to reach the equivalence point, or that we have not reached the equivalence point yet. So we're going to have to set a before and after statement. So before statement is going to tell us how many moles of hydroxide and hydronium we had, and the after, we just subtract that and see how many moles of hydronium or hydroxide we have left. And in this case, because it is a dilute solution, we're going to have moles of hydronium left from the acid, right? Okay, so let's set up our dissociations. So potassium hydroxide, that's going to completely ionize or dissociate into its potassium ions plus its hydroxide ions, right? This is going to be a 1-to-1 ratio, meaning that if we have 0.1 molar of potassium hydroxide, we also have 0.1 molar of hydronium. And that is in a 0.05 liter solution, or titrant in this case. Multiply those together, and you should get 5 times 10 to the negative 3 moles of hydroxide. Okay, so now we just do the same thing for our acid, ethanoic acid. So we have HC2, H3O2, and that's going to dissociate into H plus our ethanoate ion, so C2H3O2. Now you may be wondering that why is this completely dissociating if it is a weak acid? Well, that is due to Le Chatelier's principle, right? When we add hydroxide to this sample, what's happening is the hydroxide is reacting with this hydronium, reducing the amount of hydronium in the sample. If the amount of hydronium decreases, that means there's an imbalance in this equilibrium, meaning that there's a stress on the system, and the stress is in the right side or the product side. Meaning to overcome this stress, our reactant or ethanoic acid is going to have to dissociate more, right? It has to relieve the stress by dissociating and giving up H plus ions. And through doing that, it's basically acting like a strong acid, right? It's kind of like it's completely dissociating. Although, remember, it's still a weak acid. Due to the Chatelain's principle, it's going to act like a strong acid for the total amount of hydronium reacting with, the total amount of hydroxide reacting with hydronium. Okay, so now that we know that, we can set our 1-to-1 ratio, right? Remember, it's going to act like a strong acid for the moment being. Okay, so the 1-to-1 ratio, we're going to have 0.2 mole of our ethanoate ion per liter times 0.1 liters in this sample. You multiply those two numbers together, and you should get 0.02 moles of our hydronium. Okay, so now that we have found the quantities of the entities before the reaction, that being the hydronium and the hydroxide, we can see what happens when they react. So that being when the titrant hits the sample. So clearly 0.02, so 0.02 moles of hydronium is greater than 5 times 10 to the negative 3 moles of hydroxide. So we're going to have some excess hydronium left over, and that's going to be 0.015 moles of hydronium. Okay, so what does this mean? This means that 5 times 10 to the negative 3 moles of hydroxide reacted with 5 times 10 to the negative 3 moles of hydronium to produce a salt. The remaining hydronium, 0.015 moles of it, was unreacted. And because it was unreacted, that means it is not applied to this Le Chatelier's principle thing that we did over here. So that means this 0.015 moles of hydronium is actually 0.015 moles of our acid, right? This did not dissociate because this 0.015 moles of hydronium was not reacting with any hydroxide. So the Chatelain's principle would not apply. So we would just turn this back into 0.015 moles of our ethanoic acid. And that is in the new volume. So what is the new volume? Well, we have 0.05 liters of titrant and 0.1 liter of sample. So we just add those two guys together, right? And the new volume ends up being 0.15 liters. So that is over 0.15 liters. And you should get a concentration of 0.1 molar of our ethanoic acid during the titration process. Okay, so this 5 times 10 to the negative 3 mole quantity of our hydroxide, right? Where does that come from? Well, it comes from the potassium hydroxide, right? So all of that is going to react with 5 times 10 to the negative 3 moles of this ethanoic acid, right? Because of the Chatelain's principle. So let's write a little equation, right? So potassium hydroxide, so KOH, plus ethanoic acid, HC2H3O2. That's going to create a salt, right? The cation from the base and the anion from the acid. So potassium ethanate, I believe, plus water. Okay, so let's find the molarity of this salt. So how are we going to do that? Well, we know this is all a 1-to-1 ratio, right? We know that this and this, that's going to be 5 times 10 to the negative 3 moles, right? Because the 5 times 10 to the negative 3 moles of hydroxide that comes from 5 times 10 to the negative 3 moles of potassium hydroxide, which is going to react with our acid, right? It's going to react to 5 times 10 to the negative 3 moles of this acid. Why? Well, because Le Chatelier's principle, right? So we know that we're going to have 5 times 10 to the negative 3 moles of the salt. So potassium ethonate. And that is over the new volume, right? Once again, we're mixing the titrant and the sample. We're mixing their volumes as well. So 0.05 plus 0.1 is 0.15 liters. So 0.15 liters. And you should get a value of 1/30 molar of potassium ethonate. Okay, so if we look at this salt, potassium ethonate, you know that this potassium is going to dissociate or ionize in water, but it's not going to hydrolyze with water. What that means is it's not going to take or give an H plus proton. So it's not going to do anything to the pH. So it's going to act like a spectator ion. Why? Well, this potassium, right? It comes from a strong base, a very strong base, potassium hydroxide, meaning this is going to be a very, very, very weak conjugate acid. It's not even going to act like an acid. It's not going to donate a proton at all. Whereas, although this ethanoic acid is pretty weak, and this ethonate ion is also pretty weak, this ethonate ion is still going to dissociate a bit, and it's still going to contribute to the pH. It's still going to receive an H plus ion, contributing to the hydroxide in the solution. So we're going to have to include that in our ice table. All right, so here's the equilibrium equation, right? The ethanoic acid in equilibrium with its conjugate, the ethonate ion. And it donates a H plus ion to the water, so it's going to form hydronium, right? So initially, well, we said we had 0.1 molar of this over here, right? That's what we found. So 0.1 molar. So that's minus x, and then 0.1 minus x. And we had 1/30, or 0.03 repeating molar of the ethonate ion. So that would be minus x, and then plus x, and 1/30 plus x. And as for the hydronium, well, we had 0 initially, plus x, and that's what we're going to try and find. Okay, so what was the Ka again? Well, the Ka was 1.8 times 10 to the negative 5. This is a much greater number than both 1/30 or 0.1, making this x pretty much negligible for both of them, though still important in finding the hydronium, as we've covered before. Okay, so Ka, that's equal to 1/30x over 0.1. So 0.1 Ka is equal to 1/30 times x. So x is equal to 0.1 Ka times 30. And x is also our hydronium. So our hydronium is equal to 0.1 times the Ka, 1.8 times 10 to the negative 5, and then times 30. So we end up getting a hydronium concentration of 5.4 times 10 to the negative 5 molar. And then from here we know what to do, right? Just pH, So pH equals the negative log of the hydronium. Just plug this number here, so negative log of 5.4 times 10 to the negative 5. And we should get a pH of 4.27, showing that the solution is dilute, right? If the pH is less than 7, then it's definitely dilute. although the pH for this should be greater than 7 because we will form a basic salt, and we'll cover that in the next 2 questions, I believe, or the last question. But yeah, so that is the pH of this diluted solution. Okay, so this is question E. So this time we're going to be working with 0.2 liters of titrant. So 0.2 liters of potassium hydroxide, and this is titration. Okay, so let's do our before and after once again. So before we have, well, 0.1 moles per liter of hydroxide, right? Because potassium hydroxide 1-to-1 ratio, titrant, and we should get 0.02 moles of hydroxide. And if you remember from the previous question, we also calculated the moles of the sample before the titration. So let's do that once again. So 0.2 moles of hydronium, right? Because the 1-to-1 ratio due to Le Chatelier's principle, over 1 liter times 0.1 liters, and we end up getting 0.02 moles of hydronium. Okay, so you may notice that our hydroxide and our hydronium concentrations, or not concentrations, rather quantities, molar quantities, are equal. So what does that mean? Well, that means that they will both completely react with each other, and what we have after, right, we subtract these guys, so 0.02 minus 0.02, and that's just 0. So we have 0 moles of hydronium and hydroxide once the titrant has completely neutralized the sample. And what is that also known as? That is known as the equivalence point, when all the hydronium and the hydroxide are reacted. Okay, so all of the hydroxide and the hydronium have reacted, right? Meaning there should be no hydronium or hydroxide left in the solution. We should only have a salt and water. However, that salt that we form is not a neutral salt. That would be the case if this was a strong titration. But this is a strong base weak acid titration, so we end up forming a basic salt, meaning that it will contribute further to the pH, increasing it. So what is that salt that we end up forming? Well, as we covered in the previous question, right, we have our potassium hydroxide, in this case 0.02 moles of that, is reacting with 0.02 moles of the ethanoic acid. So it's going to react to completion. So there should be a 2 over here, my bad. And right, the cation from the base and the anion from the acid. So potassium ethanate and water. Okay, so if this was a neutral salt, then both the cation and the anion would not contribute to hydrolysis of water, meaning it would not take or give a proton to water, meaning that the pH of the solution would just be 7, or the pH of water. However, that is not the case. As we can see, this is a basic salt. Why? Well, this potassium ion, it comes from a strong base. That means that it's going to be very, very weak. It's a very, very weak acid. It's not going to do anything with the water. It's not going to take or give a proton to the water. But the ethanate ion, it comes from a pretty weak acids, right? It's still pretty weak, but its conjugate, well, it's also going to be still pretty weak, but it's going to be enough to take a proton from the water. Even though it is a weak base, it's still strong enough to hydrolyze with water, meaning it's still going to contribute to the pH of this solution after a perfect titration, or after the equivalence point is reached. Okay, so as we said before, right, this is a 1-to-1 ratio. So what does that mean? That means we have 0.02 moles of the salt, and that is over the total volume. So what is the total volume? We're adding 0.2 liters of this guy into 0.1 liters of this guy. So that's going to be 0.3 liters. So that is over 0.3 liters. And we should get a concentration of 1/15 molar. And that is of our salt. So potassium ethanate. All right, so now let's write our ice table. So we have our potassium ethanate, salt, and that is going to react with water to form its conjugate, right? HC2H3O2, or ethanoic acid, plus hydroxide, right? So what is going on with the K? Well, the K, as we said before, it's not going to hydrolyze with water. It's not going to do anything with water, so we can just cancel that out. And what we're left with is just the ethanate ion in water. And what is the ethanate ion going to do? Well, because it acts as a base, even though it's still pretty weak, it's still going to hydrolyze with water, meaning it's going to take this H plus proton, turning it back into its conjugate, or the ethanoic acid, and we're going to produce hydroxide as a result. Okay, so let's do the ice. So ICE. So initially, we said that we have 1 over 15 moles of this. So 1 over 15. And what is the change? Well, just minus x, right? And we have 1 over 15 minus x. And as we said before, that x is negligible because this 1 over 15 is a lot greater than the Ka. Okay, so what about the water? Well, the water's concentration does not change, right? Its concentration is going to be the same throughout the solution, so we just put a line. And how about the ethanoic acid? Well, that is just going to be 0 at the start, same with the hydroxide, and we're going to have plus x, and what we're looking for is the hydroxide concentration. So if we rearrange the equation, we end up getting the hydroxide concentration, which is x, so we can say that is OH, is equal to the root of the Kb times the initial ethanate ion concentration, so C2H3O2. All right, so our hydroxide concentration, that equals the square root of the Kb. Well, we have the Ka from the question, right? So the Ka is 1.8 times 10 to the negative 5. However, we need the Kb. So as we know, Ka times our Kb will equal Kw, that being the equilibrium constant for the ionization or dissociation of water. So Kb, we rearrange the equation, equals Kw over Ka. So that is 1 times 10 to the negative 14 all over 1.8 times 10 to the negative 5, and we get a Kb approximately 5.56 times 10 to the negative 10. So let's plug that in over here. So 5.56 times 10 to the negative 10. Multiply that by our ethanate ion initial concentration, or not initial concentration at equilibrium, which would be minus x, but we get rid of that because it is negligible. So just times 1 over 15, and we end up getting a hydroxide concentration of approximately 6.086 times 10 to the negative 6 molar. Okay, so now all we got to do is find the pH. So the pH is equal to 14 minus the pOH. So that is 14 minus the pOH. Well, to find the pOH, we just do a negative log of the hydroxide. So what we're saying is minus log of OH, or we can say 14 plus the log of our hydroxide concentration, right? And this is our hydroxide concentration. We just plug it in there. So 14 plus log of that. And we end up getting a final pH of 8.78. So that is the pH at the equivalence point when all of the titrant and the sample have reacted with each other. So when we added enough titrant to react with the acid. Okay, so part F, this is the final part of this question. So this time we're adding 0.25 liters of titrant, or potassium hydroxide. And as we established from the previous question, it only takes 0.2 liters of titrant to reach the equivalence point, or what is also known as a perfect titration. So if we put any more than that, then we're past the equivalence point, and this is when we end up getting a very dark solution in our acid-base lab. If you're ever doing an acid-base lab and it ends up being too dark, then this is because you passed the equivalence point and your solution is now too concentrated of, in this case, hydroxide, because we're working with a strong base, weak acid titration. All right, so we're going to do our before and after again. So initially, how many moles of hydroxide do we have? Well, we have 0.1 moles of hydroxide per liter. Remember the 1-to-1 ratio with hydroxide and potassium hydroxide times 0.25 liters in this titrant. And we end up getting 0.025 moles of hydroxide. In case you forgot, let's go over the amount of moles of the ethanoic acid again. So we have 0.2 moles of hydronium, right? The 1-to-1 ratio due to the Shalier's principle of this ethanoic acid per liter times 0.1 liters, and we end up getting 0.02 moles of hydronium. So this is going to be the first time we're going to be working with more hydroxide rather than hydronium before the titration. So 0.025 moles of hydroxide minus 0.02 moles of hydronium, and that ends up equaling 5 times 10 to the negative 3 moles of hydroxide. So all 0.02 moles of this hydronium, or the acid, right, due to the Shalier's principle, it all reacts with 0.02 moles of hydroxide. And what is left over is 5 times 10 to the negative 3 moles of this hydronium, and that is over the total volume. So over the total volume, so 0.25 liters plus 0.1 liters, that's 0.35 liters, so 0.35 liters, and we end up getting a concentration of this hydronium in the solution after the titration of 0.014 molar. Okay, so what are the entities in this solution after the titration? So as we established, we had 0.014 molar of the hydroxide, but we also form a salt, as we learned from the previous questions, right? And that salt being potassium ethanate. And that salt is going to react with water to form more hydroxide, and its conjugate, well, not the conjugate of the salt, but the conjugate of the ethanoate ion, right? This K does not hydrolyze with water. It won't take or give a proton to the water, making it useless. So we're only looking at this ethanoate ion, and it's going to take an H plus from the water, forming ethanoic acid, so HC2, H3O2, plus more hydroxide. So let's move this down a bit. Okay, so we can set up our ice. So ice, and what is the initial amount of this ethanoic acid, or just the ethanoate ion? Well, we know that all 0.02 moles of this hydronium, which comes from the ethanoic acid due to the Shalier's principle, right? All of it reacts, and as we found in the previous question, if that is true, then we just divide that by 0.3 liters, and we end up getting 1/15 molar of this potassium ethanoate, or just the ethanoate ion. So initially we have 1/15, so the change is minus x, and we have 1/15 minus x. And again, the water is not going to do anything to the concentration, so we just put a 0 or a dash. And as for the ethanoic acid, well, initially we had 0, that's going to be plus x, and that's going to be x. And for the hydronium, well, initially we had 0.014 molar. That's going to be plus x, and 0.014 plus x. Okay, so over here I wrote the Kb of our ethanoate ion, and as you can see, this is significantly smaller than 1/15, meaning we can just cancel out this x minus x. It's not going to do anything, And it's also significantly smaller than this 0.014 molar of the hydronium. So once again, the X or the plus X is not going to do anything to the hydronium, meaning that this ice table was completely useless. However, this may not always be the case. If we have a very, very small amount of hydroxide in the solution after the titration, that would be if we just pass the equivalence point, then maybe this 5.5 times 10 to the negative 6 would be significantly great enough to cause a change in the hydroxide concentration. However, as we can see, whatever our X value is, it's not going to change us one bit. So we can just neglect that X. So now all we're left to do is just find the pH using the concentration of this hydroxide, right? And that's pretty simple. So pH, as we established before, that equals 14 plus log of the hydroxide. pH equals 14 plus log of 0.014. And we end up getting a pH of 12.15. So as you can see, this solution, after the equivalence point has been passed, has a pH of 12.15, showing that it is too concentrated, way past the equivalence point. And in a lab, this would be the point where your solution turns a very dark color. All right, so these are pretty much all the variations of questions you can get for a strong weak titration, right? We can have zero titrant, we can have a dilute amount of titrant, we can have the perfect amount of titrant, that being the equivalence point, or we can go over the equivalence point, putting too much titrant or being too concentrated. So yeah, that's pretty much it.